Okay, folks, the time has come for lecture number 29. In the back, can you hear? In the front, can you hear? Excellent. Announcements. Homework number 8 is posted, and it is due next Wednesday. It's relatively small because I would like you to start focusing on Project 4. Project 4 is not due next week, but it's really big. So, the earlier you start on it, the happier you will be. I thought of a scheme of how to get you to start early. So I'm going to announce it today. There will be an early bonus point if you finish questions 1 through 12 by 1 week from today. And another early bonus point if you finish everything, including the extra credit, the day before it's due. So if you want just more points than usual, get your work done early. Any questions about Project 4? Has anybody started Project 4? Okay. Is anybody going to start Project 4 in the next week? Oh, excellent. Okay, do that, please. It's not something you want to save till the last minute. So we've actually reached a 4th chapter in this course. At first we learned about functions, then we learned about data. Now we've learned about interpreters and how they work. And Project 4 is all about building an interpreter. And you basically now understand how programming languages work, how they get used, how they work under the hood, all of that good stuff. But almost all of the examples that we've looked at throughout this course has been the computer just processing on information that was there in the computer in the first place. On small examples where, I give you one little tree and you manipulate it in some way and you give me back another little tree. And that's important for understanding how computation works, but it's different from how most programs operate out there in the world. Most computing is done by consuming data, often from other computers or other sources, in quite large quantities oftentimes, and then performing some extended computation on all of that information. So the rest of this course is about techniques that help you scale up the ideas that you've learned about on small examples to apply potentially to larger examples, and the important new ideas that arise when you do that kind of thing. So there's lots of data in the world that comes in the form of a sequence. So today we'll talk about one approach to processing sequential data that scales up to large amounts. On Monday we'll talk about another approach. Then we'll talk about some other things for the rest of the semester. But basically you should think about most things as coming in some sort of sequential format. So if you want to read all of Twitter and understand what's going on there, you can look at the posts as they were tweeted in order. Or the votes cast in an election kind of stream in a particular order as well. Or you can put them in any order you want. And that's true of all the sensor readings that you get when you're flying an airplane. So it's very common that you can think of a data set as a bunch of observations that come in a row. The positive integers are also sequential. 2 comes after 1 and 3 comes after 2. So we've been working with sequences throughout the course, but there's a problem with the way that we viewed sequences in the past. In the past, we viewed sequences as always having the following 2 properties. A sequence is supposed to have a finite length that you know in advance. That way you can put all the elements in a list at once. And it's supposed to allow element selection for any element. Now, these 2 properties don't always apply to data that you want to process. Because, for instance, the positive integers is sequential, but it goes on forever, so it doesn't have a finite length. It doesn't make sense to say what's the length of all positive integers. And it's not always the case that you can select particular elements. So with Twitter, for instance, I can start reading the Twitter stream as it's coming in right now, but it's not necessary that I have access to go back and see all the tweets that ever happened in the history of Twitter. Sometimes people don't even record the historical log of something happening like that. I think Twitter does, but it doesn't release it to the public. I see. Oh, that's interesting. Okay, so sometimes our assumptions about how sequences work are violated, and we need new ideas in order to handle things like infinite sequences or sequences that come streaming in, but we can't look up any element that we want. We can only look at stuff in order. So here's some important ideas for big data processing that we'll flesh out in the next few weeks. One is that sometimes we need an implicit representation of streams of sequential data. So instead of actually putting all the tweets that were ever tweeted on your laptop, which wouldn't work out, you can instead have a representation that lets you walk through them, or some subset of them in any order that you want, that is efficient in space, but still gives you access to the information you want. Another good idea is declarative programming languages. So we will actually learn a third programming language in this course. Besides Python and Scheme, we'll learn SQL, and we'll do that in order to understand why there are other programming languages that are called declarative, and how they work to manipulate data. And finally, right at the end of the course, we're going to talk about distributed computing. So what happens when you have multiple computers all computing stuff in coordination? And then the course will finally be over for you. Okay. Any questions before we talk about? So topic number 1 is implicit representations of sequences. Implicit sequences are useful because sometimes you can represent a sequence and manipulate it without having to explicitly say, here's the value for this element at index 0, here's the value for the element at index 1, here's the value for the element at index 2, all at once, which might be problematic for your computing resources. Okay, so what do I mean by implicit sequences? Well, an implicit sequence is a representation of sequential data that does not explicitly store all of the elements in the sequence. And we saw an example of this earlier in the course. That was the range class. Does anyone remember the range class? Okay, so the range class represents sequences of integers. It's really just representing that sequence of integers by remembering where it starts and where it ends. And any other integer in the middle you can compute. So the length and the elements are computed on demand. And this is quite a clever idea. It means that I can represent a range of arbitrary length using only 2 numbers, or a constant amount of space, which could be much more efficient than actually representing the whole list of integers explicitly. So let's just briefly remind ourselves how this works, and then we'll build our own range class so you know what it means to build your own kind of sequential implicit sequence. So the way the range works is that you have a range like from -2 to 2, and that picked out the point before -2, the point before 2, and everything in between those 2 markers was in the range. So it included -2, -1, 0, and 1, but not 2. The upper bound is excluded. Okay, let's build our own. Okay, so first of all, there's this built-in range class. I can say, what's the range from 3 to 7? And it just says it's a range from 3 to 7. And it has element 2 is 5, and the length is 4. So we want to build a class that works like that. How do we do it? Well, we need to pass in the same arguments upon construction as a range would get. So I initialize my range by saying it gets a start and an end. Okay, now what about this other behavior, like computing the length of the range, or computing a particular element in sequence? Well, the length of a range, when len is called on a user-defined instance, then it looks in that class for a special attribute named called len. We saw this before, but now you see it again. And what it's supposed to do is return the integer length of whatever this is representing. So in this case, we're representing a sequence of integers, and the length is self.end minus self.start. And how do I get an individual element? Well, there, element selection will just invoke a method with the special name getItem. We saw this before, which takes in addition to self, some argument k, which is whatever you put in the middle of square brackets, at which point it's supposed to return back the element at index k. So how do we do that? Well, we just take self.start and add k to it, and that will give us the kth element. Now, I guess there's a problem that if k is too big, that it overruns the end of the range, we're supposed to raise an index error. So we can do that too. We can say if it's the case that self.start plus k is greater than or equal to self.end, we've gone too far, folks, and so we're going to raise an index error. Okay, so let's call S here the range from 3 to 7, which is the built-in type. We'll call T the range that I just created, which is capital R from 3 to 7, and we'll see really if they are the same or not. Dash I x dot pi. So the len of S is 4, the len of T is also 4, the element at index 2 of S is 5, the element at index 2 of S is 5. So they basically are operating in the same way, and we've created our own implicit representation of a sequence of integers. S is a range, and T is, well, that's a mess. But if we wanted to fix that too, we could. We could say the string representation of this thing is just a string that says range, and then the starting and ending values. Oops. Okay, did it get better? So S is that and T is that. So now we basically have created two things that operate in the same way, and they're both implicit sequences. One of them is built in and one of them is not. Questions? Question? So the special name getItem has this particular behavior. So that's how the Python interpreter works, is every time it sees square brackets after an expression that evaluates to a user-defined instance, it goes and looks up the getItem name in the class. So those are just like linked together. That's how Python works. Yeah, if I change this to something else, like get that thing, it won't work anymore. And now it says range object does not support indexing, which is the error that you get if you don't have a getItem method. Now I just get an index error. Question? Kind of similar. Yeah, it's just properties of the language that are built in. So good question. If I set S equal to T, will that be true or false? It will be false because we haven't said anything about the equality of these two things or when they should be true or when they should be false. You can actually set the behavior of what happens when you ask whether two things are equal using another special method name. Yeah, we haven't done slicing. That's actually a different special method name. So there are features of the built-in range that we haven't written yet, like negative indexes or slices. So if you want, you can fill out the rest, but we'll have other things to do. Question in the back. The length shouldn't be negative. Oh, this is a good point. So what happens if I create a range from 7 to 3? This is the built-in range. Element at index 0 is an index error. What's the length of such a thing? Well, it's 0. Because what's in this thing? Well, nothing. Nothing is in the range from 7 to 3 because 3 is too small. That's how the built-in thing works. Now, our version is worse in the following way. If I create a range from 7 to 3, nothing breaks. If I ask what's the len of the range from 7 to 3, this function's going to compute a negative number. 3 minus 7 is negative 4. And Python's going to flip out and say, you should never do that. Len should always return something greater than or equal to 0. So if we want to get rid of this kind of error, then we should change this to an expression that always is at least 0. Okay, so now it behaves more like the built-in type. Okay, so there's an implicit sequence. Let's talk more about implicit sequences. Oftentimes, you can't get an element by its index efficiently. The only thing you can do is walk through the elements of a sequence in order. We'll see lots of examples of this as we go through the course. I'm going to start out with an example where we could find the element at index k, but it's simple enough that I figured I'd show you how it works. But sometimes it's hard to find the element at index k without just going through and generating everything in between. And if k is a large number, that can be problematic. So iterators exist in order to provide us a mechanism to walk through sequential data item by item, even if it's the case that we can't get any element we want just by its index. So this is another interface in the Python language. It's something that appears in, I'd say, all mainstream programming languages and most programming languages in general, but not all. So this is a concept that's very broadly applicable, but the syntax of how it works varies from programming language to programming language. And the way Python does it's a little weird. So I'm going to show you how Python does it so that you can feel like you know the whole language. But it is the case that not every programming language will treat this idea in the same way. Okay, so an iterator is some object. That's very normal. That's true in lots of different programming languages. Its only job is to provide the next element of a sequence every time somebody asks. In Python, the way this happens is that there's a method called __next of an iterator, and when you invoke this method, it returns the next element. There's also a built-in next function, which you can call on the iterator in order to get the next element. This is the same relationship as len and _len. Okay. Here's the thing that's a little bit quirky about Python. If there's no next element, what do? Well, in Python, Python treats this as an exceptional event. It says, oh, you asked for the next element, and there is no next element. And so it raises an exception called the built-in stop iteration exception. Okay. So the point of an iterator is to walk through elements in order. If I have a range from -2 to 2, I can call iter on it. So the built-in iter function constructs an iterator. So it invokes the iter method of the argument range, which returns a range iterator. Everything on the top of this slide is talking about how iterators work. So once you have a range iterator, it's basically going to remember what comes next. So it remembers -2 is next, and if I call next on it, it will return -2. And then it will advance the iterator, so that if I call next again, it will then return -1. And if I call next again, it will return 0. And if I call next again, it will return 1. And if I call next again, then it will raise an exception, the stop iteration exception. I spent some time drawing that stop sign for you, by the way. Okay, so the iterator's job is to not just remember the sequence, but where you are in the sequence. Yes? The range iterator object is different than the range object, and its job is to remember where you are within the range. Okay, so here I had a range. I can create an iterator out of that range by calling s. So s is still the same as it was before. Si is the range iterator. If I take si and I invoke next on it, then I'll get 3, which is the first thing. If I do it again, I'll get 4. I'll do it again, I'll get 5. So this is something that mutates the iterator every time next is invoked to move the element that comes next forward in the sequence until you reach 6, and then you raise stop iteration. If I just start this example over by creating a new si from s, I can show you that the same thing happens if I call the next function over and over again. No, iterators don't go backwards. They don't jump ahead. They don't do anything interesting. They're very basic. But that means they apply in lots and lots of different situations. So how would we create such a range iter ourselves? I said ourselves, but I'm actually going to do all the work. You still pick a start and an end, but you don't actually care about the start. What you care about is what comes next. Now, what comes next is always the start at the beginning. You do need to know the end in order to know when to stop. But unlike getItem, which does some computation but doesn't change the range in any way, the next method is not going to take in an index, but instead just return whatever's next. So if it's the case that self.next is greater than or equal to self.end, then it raises stop iteration to say there's nothing left in this iterator. Otherwise, it gets the result, which will be self.next, stores that away just long enough that we can change next to be one more than it was before, and then we return the result. Okay, so I'll start up Python. I can either create a range 3 to 7 and get its iterator. We'll call that SI. Or TI would be my range iterator that I just created from 3 to 7. Oh, I'm so bad at this game. Again. This time I did. Okay. So SI is a range iterator, TI is a range iter object. Do they behave the same way? Well, the next thing in SI is 3 and then 4, and the next thing in TI is 3 and then 4 and then 5 and then 6 and then stop. So if you wanted to build it yourself, that's how you do it. Question? So if we wanted to create an iterator over even numbers, we certainly could do that. And the way we do it is that we would create an even iter which added 2 each time instead of 1. So this kind of structure allows you to iterate over all kinds of different sequences however you want. All you have to do is write down how to get the next thing from the current thing, and you're done. Uh-huh. What do you mean? On next that prints out strings? Oh, so if you wanted to iterate through the contents of a string, how would you do that? We could use the built-in iterator over strings. Hello. We'll call this H. What's next in H? Well, that would be H, and then E, and then LL, and then O, and then we're done. And if you wanted to define your own all you'd have to do is make sure that you return the next string that you want in your sequence. Okay. Now we're going to go deep into terminology territory. There's a difference between iterators and iterable objects. An iterator is something that changes every time you say next. An iterable doesn't change typically. Sometimes it does. All depends. But the iterable's job is just to represent a sequence. So lists are iterable, and ranges are iterable, and strings are iterable. They're anything that can give you an iterator when you ask. The iterator is the thing that knows the sequence it's iterating over and where you are. And the iterable is the thing that you're iterating over. So the next thing we'll do is develop two different classes to illustrate the difference. One will be called letteriter, which is an iterator, and one will be called letters, which just represents a sequence of letters. So the letters from A to E would represent A, B, C, and D. This is a lot like range, obviously, but now we use letters instead of numbers. Letteriter is something that knows about this sequence just enough in order to go from one letter to the next. So if I create a letteriter, it will know to start at A. And if I create another letteriter, that will also start at A. And if I call next on the first one, then it's going to advance. It's going to return A, and the next thing it will return is B. But these two things are independent. They're independent because they were created as separate objects, and so they both have their own next marker. So if I ask for the next thing in the second letter iterator, then I'll get A, and then I'll get B. But that doesn't affect the first one. The first one will still return B the next time I call next. So it is possible to have multiple iterators over the same sequence. It's just different markers into the same sequence of data. Demo. So I'm not particularly attached to the range iter, and the letter iter is almost the same, so I'm just going to change it. Okay, so the letter iter still takes in the start and the ending value, but these are now letters, so I'll change the name to next letter. So I feel like I did something. If I ask for the next element, I check to see if the next letter is greater than or equal to the end. Now, you can compare letters using greater than or equal, so that's no problem at all. Otherwise, I set result equal to self.nextLetter. I want to then change the next letter to be equal to however I get the next letter, and then I'll return the result. Now, how do I get the next letter? Let's say I have B. Well, here's a way to get C from B. I get a numerical representation of B, I add 1 to it, and then I turn that back into a character representation. And now I have C. So I'll just write a line of code that does exactly that. It takes the chur of the ord of the result, adds 1, and we're done. So what did I just do? Now I have a way to iterate from all the letters from B all the way to E by creating a letteriter that starts at B, goes up to but does not include E. Once I've created such a thing, I can ask what's next. And I'll get what? B. And then C. And then D. And then error. Stop iteration. Okay, if all letters needs to do is just return an iterator, then the code's pretty simple. I say letters starts out with a start and an end value. Every time someone asks for an iterator using the built-in __iter method, I just return a new instance of the letter iterator from start to end. This is a very typical pattern, is that you can define your letter iterator and then you just return an instance of that when someone asks for the iter. Okay, if we really want B to E, one good way is to use the sequence type letters. Now, if I want to iterate through them, I need to get letter iterator number 1, which I get by calling iter on B to E. And if I make letter iterator number 2, that also is going to iterate through the same values. So what's the next thing in Li1? Well, it's B. And the next thing after that is C. And what about Li2? Well, that's still stuck at the beginning. So it's going to give me B, and then C, and then D. If I go back to Li1, the last thing it gave me was C, so the next thing should be D, and then it's finished. How we doing? Questions? I know these are simple examples, but this is useful stuff, I promise. Okay. So it turns out that iterators are used all the time in the built-in functions in Python that people use in order to perform data manipulation on a day-to-day basis. So there are just many built-in Python sequence operations that return iterators, and the way they do that is they're only going to compute the values that people actually want at the last possible moment. These are the laziest functions you've ever met. So you ask them to do something, and they say, oh yeah, I'll get to it later, and then when the deadline comes when they actually need to do the work that they said they would do, then they always do it. And that's called lazy computation. So I'm going to show you a bunch of examples, one of which is map. We've talked about that in the context of scheme. It takes in a function and some sequence, and it applies that function to each element of the sequence. But generally, it takes in anything that's iterable, so anything where you can walk through the elements in some order, and what it does is it returns an iterator over the values that you get by calling func on that x for every x in the iterable. There's a built-in filter which takes in a function and an iterable, and it iterates over only the x's for which func x returns a true value. There's something called zip. On your project, you'll build a scheme equivalent of this. It takes in 2 iterators, and it iterates over pairs. So it gives you back, if you say 1, 2, 3, 4, 5, and 6, 7, 8, 9, 10, it will give you 1, 6 as a pair, and then 2, 7 as a pair, and 3, 8 as a pair. And you can reverse the sequence using the built-in reversed. So Python programmers typically memorize all of these different ways of manipulating sequences, but all of them return iterators. Okay. So if you actually want to see what's the contents of an iterator, then you can call some constructor that puts all the elements into an explicit sequence. So list takes in any implicit sequence and makes it explicit by putting all the elements in a list. And tuple does the same thing, and there's also one called sorted, which will sort everything for you. Okay, so top half is lazy, bottom half actually creates explicit sequences. Let's see how they interact. B to E is the letters B to E. Let's say I want an uppercase B. There's an upper method. What happens if I map a function that takes some x and invokes its upper method over all the elements in B to E? I get a map object. I thought I was going to get capital B, capital C, capital D, capital... Oh, that's it. But I don't get that. Instead, I get this thing, which is actually an iterator. Let's call it M. And we'll see that if I call next on M, I get the capital B and C and D that I was looking for. So by creating something that creates an iterator, letters is an iterable that creates an iterator, I've allowed it to work with the built-in functions like map and reverse and filter that Python uses for sequence processing. Now, what was all this bit about it being lazy? Well, let me show you. I'm going to write a function called double. Double does the following things. It returns 2 times x, but just before returning 2 times x, it prints out very loudly that it's doubling x. It's saying, hey, look at me, I just doubled x. Now, I'm going to do this to show you exactly when the doubling happens. So if I double 4, the doubling happens right then. If I have a range from 3 to 7, and I map double over it, I've created a map object, but there wasn't any announcement that anything got doubled. So I said, please double everything in this sequence. And it said, yeah, I'll get to it when you need it. Now, when do you need it? Well, whenever anyone asks for the next thing, then it actually has to double the 3 to get 6, and then it gives me the 6. And not until I ask for the next thing after that do I get the 8. And if I ask, please list everything in M, then I'll get the 10 and the 12, and only then will it double 5 and double 6, where 3, 4, 5, and 6 were the things in the original range. Question? The range is unchanged. The thing we're asking the next of is an iterator, and next gets the next thing in an iterator. Question? So, why isn't M just 6, 8, 10, 12? Huh? If we want to list M, oh, I see. So you're asking, why was it the case that we only got 10 and 12, not 6 and 8? That's because every iterator changes when you ask for the next thing. So this M thing, which we called a map object, is just an iterator. I mean, it's a type of iterator. The map object is a type of iterator. And so we already consumed the 6 and the 8, which is why when we listed everything that was left in it, we only got 10 and 12. When I created a brand new map object here, it started at the beginning again, and so I got 6, 8, 10, 12. And listing consumes everything in the iterator. If I now asked what's the next thing in M, it would tell me there's nothing left. I used it all up already. Question? You don't get all the list of the results because map is lazy. Instead of giving you the list of results, it gives you an object that could give you the list of results if you ask. This is how the language is defined. The reason it's defined this way is that in this way, you could map a function over a whole bunch of stuff, and it would happen instantaneously. And then you could pass in the result of that somewhere else, and that result you might only need the first few elements instead of the whole thing. And so you'd avoid the computation of mapping double over 1,000 things if you only ask for the first few. The question is, can you access the contents of a map object without changing it? I believe the answer is no. So if you want this thing to happen all at once, you can use a list comprehension. So I could say double every x for x in the range 3 to 7. And that gives you an explicit representation. But mapping double over the range 3 to 7 doesn't do all that work. It just waits until someone actually lists the contents. Which is weird. You got to do more work. But it also makes it more flexible. When you're dealing with long sequences, you don't accidentally have to generate more than you need. Mm-hmm. Yes, that's true. But in fact, mapping never changes the thing that it maps over. It always creates something new. So let's take a range here. Let's call S this range. If I map double over S, S is still the same. If I map double over S and I put all that contents in a list, so I actually see it 6, 8, 10, 12, S is still the same. I don't know if that answered your question or not. Yeah, map is always creating something new, and it's creating an iterator over the new values. And you can put them in a list, or you can put them in a tuple, or you can never look at them at all, or you can only look at the first two. It's totally up to you as the programmer how you consume this new stream of information. Well, so map will always give you this map object, even if this is a list, 3, 4, 5, 6. It still didn't double anything. If I wanted to simulate what happens in a list comprehension, I have to call list on the map of the double of the thing, and then I get the same result as a list comprehension. The list comprehensions are convenient because they do all this stuff for you and keep everything explicit. But if you want to keep it implicit, then you can use the map and filter functions that are built into the language. Uh-huh. Map only takes iterable things. Basically, every sequence you've ever seen is iterable. String, list, tuple, and a map object is always an iterator. Question? Is what constant in time and space? The map, well, it depends what function it's applying to, but it only requires constant time to compute the next thing and constant space to remember where it is. Okay, so here we are in week whatever, 10 of this course. We're finally going to talk about how for statements work. You've probably used the for statement before because I made you, but I never really told you what it does. Here's what it does. It evaluates the header expression, which must evaluate to an iterable object. For each element in that sequence in order, it binds name to the element in the first frame of the current environment and executes the suite. Now, how does it get each element in order? Well, actually, it's constructing an iterator from the value of the expression. It is then, behind the scenes, invoking the next method on that iterator to get each element out of the iterator. So, when you execute a for statement, you're getting, you're using these two things. You just didn't know it. So, how do I write equivalent code for counts equals 1, 2, 3 for item in counts print item? It would look like this. Counts equals 1, 2, 3 items. So this is a little bit different. We have to give a name here to write it explicitly for the iterator. The iterator is the thing that remembers where we are in counts. And then, forever, I'm going to get the next item in items, which changes items to now point to something later. And then we can actually put the body of the for statement, which is print item right there. And we keep doing this until somebody raises a stop iteration. If you have a stop iteration, well, then you're done. Pass is a built-in statement that does nothing. So why would I put it there? Well, you have to put some statement in an except clause, or you'll get a syntax error. So pass is there to put something where you don't want anything at all. Okay, so now you know how a for statement works. It does a bunch of stuff behind the scenes. It creates an iterator from whatever iterable you're iterating over, and it keeps calling next on that thing until that thing raises a stop iteration, and then it's done. The objects that you create, such as the iterator, do get reclaimed so that you don't waste memory. They get reclaimed. You don't really know when, but basically whenever you know that you don't need them anymore, Python will automatically reclaim them in a process called a garbage collection. You'll learn about this if you ever take a programming languages course like 164. Whoa, so does this mean that since I created iterators and iterables for letters, I could just write a for statement for a letter in letters from B to E, print out that letter, B, C, D. Now what this does is it goes and it builds the iterator, which then calls the next many, many times until it raises stop iteration, and then it's done. So if you want to make this more exciting, we could print stop right there. Run the whole thing again. And it stopped. I guess that's more like stoop. Any questions? Okay, I'll cover one more topic. I don't really have time to cover it, but I'll cover it anyway. It's called generator functions. So a generator function is like a function, but it yields values instead of returning them. And what's special is that it can yield multiple times. So in a normal function, when you return, that means the rest of the body of the function is just gone. You never use it again. But when you yield, that means give back a value, but then keep running the body of the function, which may yield again and again and again. What you get back when you call a generator function is that you get an iterator over all of the different values that it yields. So when a generator function actually gets called, it doesn't actually return the values that are yielded. Instead, it returns an iterator that iterates over those values, which means you can do whatever you want with them. Just ask for the next thing over and over again. Okay, so here's an example. Let's say I want to create an equivalent of my letter_iter class, but just by writing a single function. Then I would write letter_generator. You can call it anything you want. You have to pass in where to start and where to end. And then you just write the logic of how to get each element in turn. While next letter is less than end, yield the next letter, and then change next letter to be one more than it was before. So this will go from B to C or C to D, etc. The thing that makes this a generator function instead of a regular function is that it contains the word yield somewhere in the body. And yield is just like return, except for it doesn't stop the execution. It just waits. It's like a pause. And it pauses until somebody asks for the next thing, at which point computation continues until you reach another yield. Question? Sure. Definitely. Okay, so I could create a letter generator. This one stops with Z, but you could imagine never stopping. That's fine too. If I ask for the next thing, what happens is it starts executing at the top of the body. It says, while next letter is less than N, yield A. And so you get A back, and the body of this function doesn't stop entirely. It just pauses. It pauses until somebody asks for the next S, at which point it computes the next letter is B, returns to the top of the while suite, the next letter is still less than Z, and so it yields B. And in this way, I've created a way to iterate over all these letters in order just by writing a function that has a yield statement in the middle. You have to keep around the frame for the generator. That's all. yeah, we don't have time for a demo. But if you want to watch the demo, there's a video online. I told you everything I have to tell you, that it's possible to create an iterator just with a function. I will see you on Monday.